All right. So today we are going to be talking about the 8-queen problem and Sudoku. So both of them, we will be using the overall same algorithm, but but they use the same algorithm in subtly different ways. So I'm going to be showing you kind of the setup and where the bulk of the work is going to be occurring. And the interesting thing is that the bulk of the work doesn't necessarily occur where you think it's gonna. You're going to assume, you'd assume it would occur in the recursive part, but no, actually the recursive part, once you get that down, is the easy part. So let me go ahead and remove what I did over here for the morning session, because I will just simply redo it later. And for the other part of the morning session, which I'll probably do without being so tired. Okay, so first off, everything I'm going to be going over doing here has already been covered in the videos. Believe it or not, there are some really good videos. At least I like to think they are really good videos of these. Specifically these last three, the recursive backtracking overview, the chess homework, and Sudoku. They're very good for this kind of thing, for this homework, and they're fairly extensive on this. That is some haircut. All right, so what we're going to be doing for, but let me just go ahead and assume that you haven't gone there yet. So that we have a common place to be starting, okay? 8 queens puzzle is a famous recursive puzzle, as I described last time. We're going to put 8 queens on a chessboard so that none can threaten each other. A queen moves like so. Okay, the queen moves like so. Where the queen can move like a rook, meaning that can move horizontally or vertically. So it can move horizontally or vertically, or like a bishop, meaning you can move diagonally. In other words, it can move in either the X or Y dimension or a combination of both, so long as the amount it moves is the same. So in chess, if we have a piece, if a piece can capture another piece, we say that piece is threatened. So in this case, if I had a pawn there, this queen is threatening that pawn, okay? The goal of the 8 queens puzzle is to place our queens is to place 8 queens on the chessboard in such a way that no queen is going to threaten any other queen, okay? So in other words, I could put a queen here and that would be valid. All right, and you see that that queen's not going to threaten it, is not threatening, nor is threatened by any. Same over here. Okay, and notice that basically that we're cutting down on a lot of space each time we add a queen. All right, so we need to, so there's a lot of solutions for this puzzle. Specifically, there's 90 or so. Sorry, 92 solutions. Here's one solution, the only symmetrical solution of the 8 queens puzzle. So that is one solution of many. There's many solutions. I just want you to generate one. Okay. Now I go over how this algorithm works in this video on a physical chessboard, where I'm doing it as a 4 queens problem. So where I'm doing it as a 4 queens problem on a 4x4. Okay. Now, the other thing we need, so overall it's well defined, but like, how do you set this up? Well, the way we want to do this with recursive backtracking is what we're going to do is that we will place a queen, is that we're going to go column by column and figure out which row to place that queen on. So for instance, again, going over to here, I'm going to look at all these spaces over here and in this first column and say, can I put a queen here? And I will go ahead and do so like this. Then the next space, I ask, okay, can I put a queen here? No. Can I put a queen here? No. What about here? If that queen wasn't existing, then sure. Okay. And so on and so forth. So now this problem and the other problems use the recursive backtracking problem, which I'm about to talk about, which is they use the recursive backtracking code, the algorithm. Sorry, words are hard apparently today. Okay. Which is, given a board and a position, we have a base case, which is such as the position is nothing less to solve. And then for each possible choice, make a choice. And this may seem a bit like weird, but let me go ahead and show you how to adapt that. Okay. So what we're going to do, so solving looks something, the code you want to solve this looks something like this: public, static, Boolean, because we're going to want to return true or false. Returning a true, and these aren't returning like true or false, like can we solve it or can we not solve it? I mean, kind of. Well, we're using them as signals as to whether or not we found a solution. True means we found a solution, which means you should tell whoever called you that we found a solution. And false means that you hit a dead end somewhere, and the partial solution you fed me is no good. Public static void solve board, and then we're going to take in not the row and the column, but the column. The idea here is that by passing in the position, we pass in the position that matters, and we always know where we are. So we're always going to know what column we need to be solving. We don't need to go and search for it. Now the base case is, now by default we'll return true, saying we need it. Sorry, return false, saying we need to backtrack. So our base case is, in this case, when do we return true? When are we done? We are done when we finished all the columns, right? So we're going to start column 0, then we're going to do column 1, column 2, column 3, column 4, column 5, all the way up to through column 7. So if we get to column 8 or higher, we're done. And in case we wanted to make this a more generalized chessboard, I'm going to go ahead and set that up. So if board dot length, since it'll always be a square, it is sorry, if column, here we go, if column is equal to board dot length. So if we've done 0, 1, 2, 3, 4, 5, 6, 7, and we get to column 8, we are done, right? Rather than just trying to go out of bounds, we're saying, oh, actually going out of bounds is good. That means we're done, right? And that reflects this. If the position is such that there's nothing left to solve, there's nothing left to solve if we go off the board. Make sense? Okay, next, for each valid possible choice. Well, what is the valid possible choice for each column? And that is, what row are we putting it in? Make sense? For int row is equal to 0. Row is less than or equal to, sorry, less than a board dot length, not less than or equal to. Board dot length row plus plus, because that is our choice. All right. And now the if valid choice. I'm going to rename this. Basically what we're going to say here is, what we're asking here is, if can place a queen in this board, on this board, in this row column combination. Make sense? So if we can put a queen here, then we'll put a, and that's where I'll leave you, because after that, it's just following the pseudocode. Okay, if I can place the queen there. Because here's actually where the bulk of the work comes in. Okay, And I'll get back to this portion in a bit, which this is where the and try to explain it, but this is where the magic happens. But as far as can place, well, we want to put down a queen on the board, okay? So we need to check some parameters if we're putting the queen down on the board, right? We put down the queen on the board. We know these directions are the queen that the queen can capture, right? Okay, but the idea here is that I'm going left to right, right? Placing the queen down, and for each column, I'm choosing which square to put the queen in, right? So if I'm enforcing that only one queen can be in a column and I'm just trying to figure out where to put that queen, I don't have to bother checking up and down, right? I don't have to bother checking up and down. It's not going to occur. Similarly, if I'm going left and right and I'm picking up each queen every time I need a backtrack, so if I'm picking up the queen if I need a backtrack, right, there's never going to be any queens to the right of me. There's only going to be queens to the left, right? Because there's never going to be queen. I'm placing queens from left to right. If I find, or rather from your perspective, I'm placing queens from left to right. If I have to backtrack, I'll pick up a queen and move back. And I'll place down a queen, but I never have to check to the right. So all I have to do is check these three directions. So in other words, I'll have three separate functions, which is return, return row safe, board, row, column, and upper left safe, board, row, column, and lower left safe, board, row, column. So, and what I'm going to do for these right now is I'm going to leave them essentially blank. I mean, obviously, not completely blank. I'm going to just simply make sure that they all finish up the same way. Return true. I'm going to assume right now that I'm going to have these all temporarily just return true. But by splitting them up like this, it means I can tackle one at a time. And by having them return true, that means that the space that I'm always checking in the recursive function is always going to be a good place to put the queen. So if all these return true, then this will return true, which means that this will always be true, which means that if you get the recursion going before we fix this up, then we can test it, just the recursion, and you'll get something that looks like this. Just queens across the top of the board, okay? Just queens across the top of the board. Make sense? Next. I think I accidentally punctured the mask. Next. All right, so next, what are we going to do? If you do the row place, sorry, it's the row safe, then it'll be kind of the 8 rooks problem, which will mean that your board output will look something like this, where they are on the same diagonal, which is perfectly fine, because you will have no, so they'll be perfectly fine. So you can solve this piece by piece. Okay. And so again, where the magic happens here is this recursive function. And it takes some getting used to. But the idea here is that we put down the queen, and then we say, let's go to the next column. And if that column returns true, that means it was either at the end or the column that it eventually called got to the end. And that means that where we are, the partial solution that we're currently at led to a complete solution. So return true to tell whoever called us, right? So column 8 is going to reply to column 8 doesn't exist, it will return true. Column 7 will report to column 6 to return true. column 6 will report to column 7, column 5 to return true, column 5 will report back to column 4 to return true, and so on and so forth. If, however, we get to this return false, or sorry, if we got, however, a false back, that means that whoever we hit got to a dead end. So we pick up our queen and we go to the next row in that column. And then we keep trying again and again and again. And if none of our rows work, that's when we return false. That's when we say to the person who called us, hey, you're going to have to adjust where the queen is in your column, because that didn't lead anywhere. That was a no-go. Now, the same algorithm is used for the game of Sudoku, which is a Japanese word, but that comes from a Japanese game, but not necessarily in itself Japanese. Like, they're like a lot of things, like theories of mathematics. They wrap up all over history. So, and Sudoku is one of those games. Sudoku is literally is originally a number place, and I can say from experience that just like the Israelis, the Japanese love making long phrases into shorter words for titles. So Sudoku is short for Suji wa dokushin ni kagiru, which is the digits must be single, or the digits are limited to one occurrence. So we can see there's some kind of a puzzle. There's similar things coming out of France. But anyway, the modern rendition of this puzzle looks like this. You'll get something like this as a puzzle. Okay, and the way this works, and this is what a solution to this puzzle looks like. And the idea here is that to complete the puzzle, you place the numbers 1 through 9 in each row and column such that each number only occurs once. So here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, in that row. And the next row, it only occurs once. And the next row only comes once. And in each column, the numbers only occur once. Okay, each column, the numbers only occur once. But there's also one more twist. You see how it's split up into a 3x3 grid? Each of those 3x3 grids can only have each number once. So over here, you'll notice that in this upper middle 3x3, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and it only occurs once there. So you can already see the kind of can place or is valid kind of playing out here. You got to check if the row is valid in the column, in the row, and in the 3x3 square. The 3x3 square being the hardest one to figure out. Okay. So this one, and so this is it's a wonderful game. It's kind of elegant. You can figure out a lot of things here. I was doing this. So like it's all about, just kind of the, using logic and the elegance of logic. Like we've got 2, there's a 2 here, right? So first off, there's a 2 here in this column. So that means that there can't be a 2 over here, which means we can't put a 2 over here, right? Can't put the 2 in the highlighted square. Similarly, there's a 2 over here, which means that a 2 can't be here. So by process of elimination, a 2 has to go here, right? Everybody see that? Can't go here. Can't go in these squares, so 2 has to go here. And a 2 has to occur once in this 3x3 square. Okay, and it just kind of, and you can use, kind of the computer to help you out to figure out like, okay, narrowing down the possibilities so that you can see them, or you can mark them down yourself. But it's fun and elegant. And this one's an easy puzzle. Hard ones have less choices and none of the candidates necessary, and you don't necessarily get anything. Okay, so we get 1 for free here, but it doesn't necessarily help us, I don't think. Okay, so 3 doesn't always help us as much as we'd like. At some point in the harder puzzles, you have to start guessing. You have to start making guesses. And seeing where that logic takes you. However, the solution we use about as subtle as a giant club. Subtlety is not what we are doing here for our solution. Elegance is not what we are doing. It is as elegant as a rhinoceros in a china factory. So this is the way the recursive backtracking algorithm works. And so this is the big point about recursive backtracking algorithms. Recursive backtracking algorithm says this puzzle is way too big and way too hard for me to solve. I can't look at this big thing, otherwise my brain's just going to explode, because I am I am a dumb human who just cannot even on some days, So instead, what I'm going to do is I'm going to look at each individual square. I'm going to treat each individual square as its own puzzle, as its own thing, and go process by process of each individual square. I'm going to try to reduce this big problem into a bunch of tiny localized problems. And I'm just going to start from the top left and go to the bottom right. So, okay, that square's filled, that square's filled, that square's filled. I don't have to do anything there. Okay, let's see over here. Let me try 1. Okay, that doesn't work. What about 2? That doesn't work. What about 3? That doesn't work. What about 4? 4 works. So I'm going to go on to the next square. Okay, 1, 2. That works. Keep going on. 1, 2, 3, 4, 5, 6. That works. 1, 2, 3, 4. 3. That okay. I got to the end of the column. I'm going to go to the next row, set my column equal to 0, and now empty square. 1, 2, 3, 4, 5, 6. 1, 2, 1. And now I should get to a dead end over here, I think. 8, 9. Yes, I'm in a dead end now. So that square doesn't work. So I'm going to unmark it, go back here, and yell at this one and say, hey, you dummy, a 1 can't go there. It led me to a dead end. Now, this isn't the same as brute forcing, because brute forcing would have tried 1 over here and then like 1 over here, right? It would have continued on with an impossible solution. Here, we're just trimming out if there's any possible thing like this, we don't bother continuing with that branch. We just trim it out, which cuts down on the number of permutations we have to check. 1, 2, 3, 4, 5, 6, 7, 8. And now we see that works. And now we go to the next one. And so on and so forth until we get to the puzzle. Sometimes we have to back up a whole lot. Sometimes we don't have to back up. Sometimes we barely have to back up at all. Right here, I'm going on to the next one. And of course, the easier the puzzle is, the easier, the less chance there is to backtracking. Okay, everybody see just kind of how this works? And of course, once I'm done here, done. So unlike the other one, we kind of have 3 base cases over here. Okay, which is so first off, public, static, Boolean. And so part of the reason I do this is I've seen students where they just pass in the board and then they look for the next empty space. I don't want you to do that. Again, we're trying to reduce everything to make everything a local decision. That means that I should be taking in an int row and an int column. I've got 2 coordinates for my position, but it's still a position, right? And here's what I'm going to do. So first off, return false by default. By default, I hit a dead end, so I'm going to have to backtrack. And then I'm going to ask myself 2 questions. Sorry, I have 3 base cases over here, essentially. Okay, the first one is if column equal, and they don't all necessarily mean I return true. If column is equal to board.length. In other words, if the column went out of bound. And we saw what happened with if the column went out of bound. If the column went out of bound, I go to the next row, right? Next, if my row goes out of bound, that means I'm done with the puzzle, right? If row equals board.length, and here I'm using board.length rather than 9 because, in case you want to make it bigger. like a 16 by 16. I'm sure that would work. It's just the larger search space. Okay, and then we're done here. This is our end condition. And finally, base case. And again, base cases are just non-recursive cases, really, things you don't have to think about. So technically, we only have 2 base cases, and then we have 1 simple recursive case, which is the one that a lot of students have a bit of trouble with, which is what do I do if I already have a square that's occupied? And the answer is be lazy as you can be. And it takes a while to figure out the easiest way to be lazy about this kind of thing. And the way to, and by be lazy, I mean, it's not your problem, it's already filled. So if board row column is not equal to 0. So 0 in this case is empty, right? So if it's not empty, then I want to do something else. And that one I'll give to you. You just return board, sorry, you return solve board row call +1, because we're going left to right across, because we're going across left to right on the columns, right? So that's why the call +1. Okay, and then you get back into the pseudocode. Okay. And these kind of problems are fun, or are easy to do. And I know it doesn't seem like it, and not necessarily at the first glance, but this is actually exactly the kind of same algorithm that you used for your maze problem, for doing depth first search. Depth first search is the recursive backtracking algorithm. Here, we're using the stack implicitly by using a runtime stack. Bit more mathematically elegant than using a actual physical stack. There's pretty much everything you can do with recursion can be instead done with the regular stack. There might be some weird recursive math functions that you can't necessarily emulate using recursion, but using a stack. But as far as I can tell, I haven't seen a problem that you can't use a stack on, but a lot of times this recursive process is nice. Also, if you're working in an IDE, when you do a recursive call, you notice that you've got that it gets that it has a spinny kind of icon there. Recursion is, again, extremely powerful and useful. And it's important that you master it, because when we get into trees, those are recursive data structures, meaning that we'll be solving them they're both, basically every tree is made up of subtrees, and the problems can be best solved by considering the current node you're on as the root of its own tree or subtree, which makes more sense when we get there. So that's why the second exam will focus a lot on trees. And again, the second exam isn't anytime soon. This is week 11. Sorry, week 7. We'll be doing it on week 11, most likely. And that will be some time when we get back. And that will be week 11 when we get back. Like, we're not counting the spring break as part of that week, because that would just mess up the counting, I feel, because it's not actual class time. All right. Now with that, I'm sure a lot of you have demos to do. So I am up for taking demos. All right, so stop share.